Good day, and you're most welcome to today's session of the CNPS. It's one of our Saturday technical sessions, where we have an invited speaker. This might happen roughly fortnightly. And today we're delighted to reintroduce to you, because he has spoken to us before, actually, Joe Sorge. And he'll be dealing with the famous or infamous Sagnac effect, which, according to my humble view, is a bit of a thorn in the side of the conventional relativists. Well, anyway, one of the things about the Sagnac effect, which I say is a bit embarrassing to mainstream science, is that counter to what one might expect, the effect is independent of the refractive index of the medium. So in other words, instead of having a spinning disk, well, Joe will be going into all of these. I'll try not to steal his thunder too much, but as far as I can see, instead of having the lasers or whatever light beams going around in air, if you put a refractive medium in there, you would expect the light to be slowed down, therefore the time, the circuit time, to be different. But actually what it turns out is that it's independent of the refractive index of the medium through which the light is going. So the title which Joe chose today is Deconstruction Light Speeds in Moving Refractive Media. And the information is the independence of the Sagnac phase shift or time shift from refractive index can appear puzzling, yes, particularly when compared with the Fizeau experiment, where refractive index plays a central role. So when the Fizeau experiment through moving water, it's highly dependent on the refractive index, and you get a drag coefficient. An intuitive basis for this difference is provided by decomposing the light transit time in a moving dielectric into vacuum transit, refractive delay, and motion-induced differential distance. Now, to me, that's Joe's new development, which is rather heuristic. He's trying to, as far as I can see, give a heuristic interpretation of the result, the analytical result, that it's independent of refractive media. So, without further ado, I hope I haven't really spoiled what Joe's going to say. Just try to put it in perspective. What we'll do is I'll be bringing Joe up in a moment, and we'll just have a brief chat. I'll then hand over to Joe to introduce the topic and make as many preliminary remarks as he wishes. And I know he has slides here, which actually in the rehearsal he was able to put up, so I don't have to put up the slides, but I have them here as a backup. So Joe will be able to go through the slides. I had a quick look at them. They're very clear, and he'll be talking to those. And then normally we have an hour plus or minus 15 minutes to talk, probably uninterrupted. However, I will be looking at the comments coming in, both from the social media and also from the green room. In fact, I should really suit the action to the words. There are 4 comments in already. What are those? Yeah, James started putting the comments in. We'll be dealing with those later, and we'll get Joe to answer maybe some of these questions, and then we'll have a fuller discussion maybe with some of the people in the green room, maybe some back and forth, and then at the very end I'll give Joe a period at the very end, actually, a couple of minutes if he wishes, to summarize and maybe introduce any new concepts which he didn't address in his talk, owing to some questions which might have been asked or the discussion. And then I'll close the meeting myself. I do say, I think this hasn't actually happened, but if there are any really urgent matters which cannot wait until the question session, if you put a comment in, this is really urgent, I think I don't understand what Joe said or something, or surely this contradicts something. Well, I'm sure Joe would forgive us in extremis if we did interrupt him. But unless that happens, we'll allow him to speak uninterrupted for the first hour or so. So good day, Joe. Good morning to you. You're in. Where are you in North America, in the US?
At the moment, I'm in Las Vegas.
Okay, okay.
I don't know if you know, but I tried to retire.
You tried to retire. You gone dead. Mute. Can't hear you. It was all right until just a moment ago. What's happened to
How
that?
about now?
Perfect, perfect, perfect. Yeah.
Now you can hear me? Okay, good.
Yeah. So you were going to retire, but you haven't. Is that it?
I tried to retire about 10 years ago and I failed at it. And so I took on another career and I've been building apartments in Las Vegas, apartment buildings. So
okay.
yeah, I have a whole development team, and most of my day is involved in fielding questions from staff of, should we call the plumber to deal with this? And should we get a new light bulb installed somewhere and things like that? It's crazy. But so very far away from physics, but I love the physics. It's my hobby, and it gets my mind stimulated.
And I think we have to say that most of us are amateurs. I mean, maybe we were professionals in our former lives, but I'm retired now, so we are amateurs. And I'm going out to nature, or I'm doing artistic studies or something. God knows what I'm doing. Right, I'm in a writers group which meets and so on, and then I do physics. Right. And I think that there's a good what shall I say, record there. Somebody like Spinoza, one of the greatest philosophers ever, he just spent the day grinding lenses, you probably know, and in the evening time he was free. So it's always good to have a break. So we're looking forward to your talk. And you've done a lot of videos actually, and feel free to give links to those to the participants, because they may wish to look at those at their leisure. You're a very prolific and you're a very clear speaker. I'm not just saying that because you're the guest today. So what I shall do is I shall disappear myself. Now, what that means is that if you call me, you won't get a response for a moment, because it takes me a second to go back. I'll be mute. But if you need me, just say, Ian, I'll come back. It just might take a second to come back. I'm going to give you the floor. And then if you want your slides up, just say, Ian, please put this. No, sorry. Yes, I have to put them up. You've actually arranged, but I have to put them up.
Okay.
But the beauty about this system is you'll have control, so you'll be able to advance. But if there are any problems, just call for me. Okay.
Okay.
So I'm disappearing now.
Okay. Well, thank you, Ian. I appreciate that. Appreciate the introduction. And I just will say ahead of time that, what motivated me here was a friend of mine had studied Einstein in high school, and he asked me to explain it to him. And I said, well, I really don't understand it, but I'll do a little bit of reading. And one of the things my friend said to me is that it's remarkable that light always goes at the same speed for everybody. And that just didn't sit well with me. I just felt like there had to be some other explanation. And so I began to dig into it, and that eventually led to the work that I'm about to present here. And I just also want to say that, this did get published in a peer-reviewed journal, European Journal of Physics. And I think the only reason it got published is because they didn't know who I was. They do double-blind peer review, and so the reviewers didn't know where the paper was coming from, which gave me a fighting chance, because usually when I've submitted papers in the past, the editors reject them without even reviewing them. So anyway, so at least 3 people in the world have thought this work is worth looking at. So I'm assuming you can all see my slides now, or Ian, maybe it's time to put them up and just confirm that you can see them.
Well, I think if I can see them, everybody should be able to. And okay. If anybody can't see the slides, just put a comment in. But I'm sure it's all right, Joe.
Great. Okay. So I'm going to proceed with the slides. So the question is, why does light speed change in refractive media? And I don't think the answer is really known at the atomic level or at the wave level. Some theories say that it has to do with charges interfering with electromagnetic radiation. It also could be that the molecules of the medium are somehow acting as, I just call them obstructions, not knowing what the mechanism is. It also could possibly be that the atoms or molecules actually absorb electromagnetic radiation and then re-emit it. And I'm not committing to any of those models. Really, what I'm about to show you is agnostic with respect to the mechanism, but nevertheless, I just want to check that you can hear me again. It said audio disabled.
We lost you for a couple of seconds there, Joe. And just before you said, "Can I hear you?" it was a break. So I wonder, was there a problem there?
Yeah, I got a warning on my screen said audio disabled, and I don't know why that's happening, but I'll try to keep an eye out for it. So
thank you.
Anyway, so I'm agnostic with respect to the mechanism, but I did find something interesting. So let's talk about just the basics of refraction. When a medium is stationary, the speed of light is c divided by n, where n is the refractive index. And many media have been examined and a value of n assigned to them. And the question that was raised several hundred years ago was, does light speed change if the medium is moving? And the answer is yes. And this was shown by Fizeau in 1859 and Sagnac in a different way in 1913. So what Fizeau did in 1859 is he set up a light path and that goes through a water tube where the water is moving. And so what we have here is water flowing from the bottom around this path and up the top. And I forget how fast the water was going. It was, for water speed, it was like a fast hose. So it was not anywhere near relativistic speeds. We're talking about, meters per second. And we have a light signal coming in here from the left and a beam splitter. And the beam splitter allows some of the light to go through, straight through, and that would be going against the direction of water motion. And it hits a mirror and another beam splitter mirror, and it can go back around this way, again, against the direction of motion. Oops. Against the direction of motion, hit another mirror, come back up, and reach the beam splitter. And the other light path, if it comes in and is reflected by the beam splitter downward, then it goes around the circuit in the direction of water motion. So, and then it can recombine with that original signal. And in this diagram, they have another beam splitter here. So you can get recombination occurring here or here between the two light paths. And what Fizeau expected is that the speed of light would be c over n, which is the speed in the stationary medium, plus or minus the speed of the water v. But that's not what he found. Instead, he found that the speed of light was c over n plus or minus v times approximately 1 minus 1 over n squared, as opposed to what his original belief was. And this has been referred to as partial drag, but no one was happy with this answer. One thing that they did recognize, it did match a formula proposed by Fresnel in the early 1800s. And so there was something to it, but they weren't really happy with the mechanism. How could the water be partially dragging the light? So there wasn't a lot of new thought on this until 1907. Max von Laue proposed that what was happening is we were experiencing relativistic velocity addition. I guess he was a student of Einstein's or a colleague of Einstein's, I'm not sure. But he saw that if you took Einstein's relativistic velocity addition formula, which is the speed of light in what's called the rest frame, and I just want to pause here. I don't like the names that scientists have assigned to the frames, but I'm going to use it anyway, not to confuse people. But in my way of viewing things, there's a stationary frame, and then there's a moving frame. And in the physics books, the stationary frame would be like the train station, the moving frame would be the train. But the train is called the rest frame in relativity because the relativistic work typically talks about items that are at rest within the train. So they call the train the rest frame and the station the stationary frame. Sorry. So this would be the speed of light in the rest frame. This would be the speed of the rest frame relative to the stationary frame, v. And I don't know why I'm having trouble here. And then divide it by 1 plus the rest frame speed times the speed of the rest frame over c squared. That's Einstein's relativistic velocity addition formula. And it really just comes from taking the Lorentz transforms and dividing the distance transform by the time transform. And this is what you get. So von Laue said, okay, the speed of light in the rest frame is c over n. In other words, when the medium is at rest, light goes at speed c over n, plus or minus the speed of Fizeau's water, v, divided by 1, plus or minus v. It would be the speed of light, c over n, times v over c squared, which turns out to be v over c times n. And then this turns out to be approximately equal to c over n plus or minus v times 1 minus 1 over n squared. And so von Laue figured, okay, he came up with the answer. This is why we're getting this crazy formula. It's a result of Einstein's relativistic velocity addition formula. I just want to point out here that, and I have a warning thing here. Let's see. Okay. I just want to point out that these speeds are greatly less than, or very, very slow compared to speed c. So calling this a relativistic effect is stretching things to the extreme. Nevertheless, because of the agreement with the formula, this became the accepted explanation. All right, now in 1913, George Sagnac came along and he did a slightly different experiment. One thing I want to point out is in the Fizeau experiment, the laboratory frame, the water is moving through the laboratory frame. So the water is what we've been calling the rest frame, it's the train frame, and the laboratory is the station. And water is moving through the station in the Fizeau experiment. And I will also point out that the length of the light path is constant in the Fizeau experiment relative to the laboratory. But the light path relative to the moving water changes as the water rushes through the laboratory. So as the light goes through in this direction, it's going through a longer light path. As opposed to going in this direction, it's going through, I'm sorry, I had that wrong. It's going through a shorter light path in this direction and a longer light path in this direction, because in the clockwise direction, it's fighting the current, whereas in the counterclockwise direction, it's flowing with the current. And by the way, if you do have questions, just stop me at any time. If there's something I said that's not clear, please stop me. Okay. Sagnac turned things upside down. He set up an experiment where we have a light source and a beam splitter. And if we go through the beam splitter, we're going in the counterclockwise direction back to the beam splitter. But if we're reflected by the beam splitter, we're going in the clockwise direction back to the beam splitter. And what we have here are mirrors. And this was originally done in air. It's since been done in vacuum, and it's been done in refractive media, but in the original experiment, it was simply done in air. And what Sagnac did is he put this whole thing on a rotating platform. So the whole thing spins here drawn in the counterclockwise direction. Sorry, in the counterclockwise direction. And so what we're effectively getting is that in the rest frame, the beam of light that's going in the counterclockwise direction is drawn there, but in the laboratory frame, we have a slight movement of the mirror in the transit time from the original beam splitter to the mirror. And so we get an increase in the path of the light as it's going around and back to the beam splitter relative to the laboratory. But relative to the rest frame, we have normal lengths going around. And then in the opposite direction, okay, why am I not? I've suddenly lost control of, oh boy, here we go. In the other direction, in the clockwise direction, again, in the rest frame, lengths are preserved, but in the laboratory frame, because the platform is spinning relative to the laboratory, the lengths are shortened. And so when we make the full circuit around in the clockwise direction, we get a shorter overall path relative to the laboratory, but in the counterclockwise direction, we get a longer overall path relative to the laboratory. Okay, but in the rest frame, if you were on the platform rotating with it and you didn't know you were rotating, you would assume that the path lengths are the same in both directions. And what the result came out is that you actually get a fringe shift here at the beam splitter for the two light paths, the clockwise and counterclockwise light paths, end up taking different amounts of time to get around the path. And if you look at it from the laboratory frame, you would say, okay, yeah, that's fine, because you have a longer path going this way and a shorter path going this way, so it should take different amounts of time. But if you are in the frame, in the rest frame, and you recognize that there's a fringe shift at the beam splitter, you're perplexed, because to you, if you believe in Einstein's constant light speed, well, then light should have traveled at the same speed in both directions from your perspective, and you should not be seeing a fringe shift. And in fact, if you believe von Lau, where he assumed that light speed is c over n for a refractive medium in the rest frame, then again, you should not have seen a fringe shift, because in theory, light is going around the path in both directions at speed c over n. And so his velocity addition formula, while it yields a differential speed in the laboratory frame, it should have yielded a constant speed in the rest frame here, but it does not. And that's why Sagnac caused a stir, because Sagnac said, well, I've kind of proven that part of special relativity is wrong, because I'm showing that you actually get different light speeds in the rest frame. So what happened is physicists decided they were going to ignore that because it was inconvenient. And what they actually did is they criticized the experiment, because they said, well, this is not an inertial reference frame. It's spinning, it's accelerating, so it's outside the scope of special relativity, and we're going to ignore it because it's not an inertial frame. And so for many years, it was simply ignored. And I've heard people say that physics classes typically do not teach Sagnac, and some physics textbooks don't even touch on it because, again, it creates a potential problem, a problem that I think I've worked out here. So then in 2003 and 2004, these scientists, Wang, Zhang, and Yao, did a very interesting experiment. They did a Sagnac experiment, but they did it in a linear fashion as opposed to a rotating platform. And this is one of the worst figures that I've tried to figure out. But essentially what they're doing is they're taking a fiber optic cable and they're putting it in this structure they call a clothesline. And then they have a fiber optic detector here. And they're looking for a fringe shift. They send the light in both directions. They spin the clothesline, and then they look for a fringe shift over here. And the idea is that light is principally going in a linear direction through the fiber optic that's spinning around the close. I shouldn't say spinning. That's being circulated along the clothesline, and so we have mostly a linear path. And what they found is they got a Sagnac effect, in that it was proportional to the length of the linear portion of the clothesline and multiplied by the speed of the clothesline. So it's, I think I just have it. Sorry, again, here we go. And this is just my drawing of what the linear Sagnac effect is doing. So in the rest frame, so in the frame of the moving medium that's inside of the fiber optic, which is glass, most fiber optic cables are filled with glass. In that frame, if we take the two light signals and we go around the circuit in the rest frame, well, the length of the rest frame changes configuration, but it does not change its length. So the circuit to go from A around and back to A in either direction is the same length in the rest frame. We just get a configuration change of the pathway. But in the laboratory frame, this signal here is going to point E, and this signal is going to point C. But as the configuration changes, this dotted path length, does not have to go as far to reach point C, because point C is moving toward it. Yet this clockwise path started at C, but it has to go farther to get to point E, because point E is moving away from it. And so we get this trapezoidal structure in the laboratory frame, and we get a longer path in the laboratory frame clockwise and a shorter trapezoid counterclockwise. And this is essentially what Wang and et al. Had done, and they showed that the speed in the laboratory frame is the length of the path, which I have it as dx prime here because I typically consider the rest frame my prime frame and the stationary frame my unprimed frame. So this is the length of the path in the prime frame, which, as I said, is constant, times speed v of the movement of the path. So this would be the speed of the clothesline. And they actually found that they didn't have to move the clothesline very quickly at all in order to see the fringe shift. And that's because it's a first order effect. It's linearly proportional to speed v, as opposed to many other experiments in relativity where it's a second order effect and much more difficult to measure. So a Sagnac effect is a first order effect and very visible at low speeds. So what does this mean with respect to special relativity? Well, there's something about special relativity that, that not too many people appreciate, and that is when Einstein described the setup in special relativity, he described two clocks, clock A and clock B, separated by a distance, and in the rest frame, I call that dx prime. And Einstein described a way of synchronizing the clocks, and he said, take a light signal from clock A, send it down to clock B, reflect it with a mirror, excuse me, at clock B, send it back to clock A, and then measure the round trip time, divide that in half, and then attribute half of that propagation time to clock B and half to getting to clock B, and the other half to returning from clock B to clock A. So even if the two paths took different amounts of time, he simply averaged the round trip time and attributed only half of it to the downstream trip and the other half to the upstream trip. And that's in the 1905 paper. Most people don't understand that or appreciate that. But what it leads to a difference in the settings of these two clocks. So if you are looking at the clocks from the stationary frame, in theory, you would observe that these clocks are not reporting the same time of day because of this method of synchronization. If the rest frame, I hate the word rest frame, but if the rest frame is moving relative to the stationary frame, then this method of clock synchronization is going to lead to an offset between the readings of these two clocks. So if this clock is reading t prime 0 in the rest frame, this clock will be reading that same time minus v times dx prime over c squared. And some of you may recognize this as a term that's in the Lorentz transforms. And I don't think Lorentz ever knew what this term really meant. He called it local time. I think he and, I don't want to speculate too much, but I think he and Poincaré were bringing up this concept of local time, and Einstein incorporated it into special relativity. And Einstein came up with this clock synchronization explanation for local time. But again, to overemphasize this because it's important, in special relativity, if there's a moving frame, one of the clocks, if it reads t0, the other clock is offset by negative v times dx prime over c squared. And one of the cover-ups in special relativity is they say, well, if you're in the moving frame, you don't know this. If you're in the rest frame, you don't know this. You think all the clocks are reporting the same. And in fact, many treatments of special relativity say, in fact, all the clocks do report the same time everywhere in the rest frame, even though from the moving frame you can see that they don't. I think that's stretching the truth. I think, yes, if you use Einstein's method to calibrate those clocks, you are going to get differential readings. You just don't know it if you're in the rest frame because they're too far apart for you to take simultaneous readings. What goes on in a Fizeau or a Sagnac experiment is you only have one clock, and you send the light signal on a one-way trip. See, in Einstein setup, you do a two-way trip, and you average the elapsed times. In a Sagnac experiment or in a Fizeau experiment, you have a one-way trip around a cycle, and the clock is the beam splitter. So you split the light signal, you send it this way, you send it that way, you recombine it, and the beam splitter is creating a fringe shift, which is essentially measuring the travel times in the the differential travel times in the two directions. So it's not a clock in the sense of it's giving you a time reading, it's just telling you that the two signals took different amounts of elapsed time. Okay, so now we go into my paper in the European Journal of Physics, and where I start with is I take the Lorentz dt prime formula, the rest frame formula, and I just rewrite it in a mixed frame format. You really can get this by taking the dt formula and reformatting it like this. And so what you get is dt prime equals dt over gamma minus that clock offset term v times dx prime over c squared. So there's nothing new here. I've just rearranged the Lorentz time, the dt time formula in this format. But I did it to point out that dt prime is a combination of time in the stationary frame over gamma for time dilation, because stationary clocks tick faster than rest frame clocks. And so we divide by gamma to make them equate to each other. But then we put in the clock offset term that Einstein and Lorentz put in, which is that local time term. But in a Sagnac or a Fizeau experiment, there is no second clock to put a time offset into. And so we can simply eliminate that in a Sagnac or Fizeau experiment. And so we have dt prime here, and I put a little star just to indicate that there's no clock offset term in this formula. And we just simply use time dilation, dt over gamma, as a reference between the two times. And this was published in the late 50s by Tangerlini, and then expanded upon by Soleri in the 70s. And I know one of our members of the group is a strong adherent to Soleri, and I think there's a lot of wisdom in the Soleri analysis, but one should not emphasize that one should not say it's different physics. It's the same physics, just using different clocks. So, or a different clock coordination scheme. In the Soleri and Tangerlini coordination scheme, all the clocks report the same time of day everywhere. It's more Newtonian. Whereas in the Einstein configuration, there's a gradient of clocks along the direction of motion, or I should say a gradient of clock readings along the direction of motion. But my point in the paper was that the Lorentz transform is inappropriate for a Fizeau or a Sagnac setup because there is only one clock, and there's no sense in creating a clock offset because there's only one clock, and you cannot offset a clock against itself, even though I've come across 3 papers in the literature that try to squeeze the Lorentz transforms into the analysis of Fizeau and Sagnac, and it's comical how they can't think outside the box. You know, I learned something in college and math classes. There were these things called branch cuts. If you take the logarithm of a negative number, you can get a number, but you get it's almost an infinite number of solutions, and each solution is called it's supposedly on a different branch. And when you go around the circle once, you jump to a new branch. Well, this is essentially they're trying to explain that in a Sagnac setup, you actually have clocks on different branches, and you jump from branch to branch. It's taking a square peg and shoving it into a round hole. What's really going on is you have one clock, you don't need this term, and you just use time dilation. Okay, and then we now weave in refractive index. So this is essentially Lorentz's dt formula written a little bit differently. There's typically a gamma out in front of the dt formula, and then it's dt prime plus v times dx prime over c squared. This is the same thing. It's dx prime over c brought out in front. And then we have the refractive index here, which you don't typically see in a Lorentz formula, but that's where it belongs. And then we have beta v over c. And so just think of this as the Lorentz time formula with refractive index included. Okay, and so to compute a fringe shift, we want to take the difference in that time formula. So we want the difference in time of arrival times for our 2 light signals, delta t, times the frequency of the light will give you the fringe shift. So we take delta t times frequency, and here's our delta t using that time formula. This time formula here, we just subtract the positive, the negative from the positive, and then multiply by frequency, and we get 2 gamma times frequency times v dx prime over c squared. And this is actually the fringe shift in a Sagnac experiment, written differently. Oftentimes in Sagnac experiments, they talk about the area of the disk that's going around in circles. And so you'll see an angular frequency in a Sagnac formula. You'll also see the area that's being traced out. It all boils down to the same thing. The formulas are identical when you just rewrite them with different variables. And the reason I write it this way is because it fits better with the Einstein explanation. And also it fits with the Wang linear Sagnac effect, because in Wang we have v times dx prime. And so it makes it just easier to understand. And again, Wang et al. Showed that the effect is proportional to v times dx prime. So if you increase the length of the clothesline, you get a greater fringe shift. If you increase the speed of the clothesline, you get a greater fringe shift, and it's the product of the two. Okay. Note that there's no refractive index in this formula. And the reason is because if you take dt plus and subtract dt minus, well, the refractive term is out in front here, and so you subtract it from itself. Whereas the beta term is plus or minus, because in the counterclockwise direction, beta is negative, in the clockwise direction, beta is positive. And so when you subtract a negative from a negative, you get 2 times the beta term. So we're really looking at the beta term here. This is what a Sagnac experiment detects. It detects a first order velocity effect with the comparing the counterpropagating signals. Now, what's interesting is dx prime is the length of the path in the rest frame. And as I showed earlier, the rest frame path does not change length. It's the laboratory frame that changes length. And so what we're getting here is for a constant length path, we're getting two propagation times, which, length divided by time is speed. So essentially we're getting two speeds. We're getting one speed in the positive direction and a different speed in the negative direction, which of course violates one of the postulates of special relativity. But now we can see the reason for it. And the reason for it is if in fact the speed downstream in an Einstein setup were different than the speed in the upstream setup, well, this local time clock offset exactly compensates for that difference. Because remember, the clocks were coordinated with light. So if you use light to coordinate the clocks and you create this offset, and then you have the actual differential time in your experiment, but the offset is there, it's going to look like it propagated at the same speed in both directions. Sagnac and Fizeau reveal that that's not the case because there's only one clock. You can't have an offset, and so they actually reveal the differential light speeds. Okay. So let's see, this may be recapping what I just said. So von Lau and Einstein assume that light speed is isotropic in the rest frame, meaning c over n in both orientations. But because we're getting different travel times in the rest frame, we're essentially showing that we're getting anisotropic light speed in the rest frame. You could easily say, defenders of special relativity can say, well, you haven't really discovered anything new here. You just took away one of the clocks and you're revealing that relative to your moving frame, light is traveling at different speeds relative to that moving frame, but it's still traveling at speed c relative to the universe, and you're merely moving your clock relative to it, and that's why you're seeing these different speeds. And I say, I agree. That's true, but it's starting to point toward a preferred reference frame, the universal reference frame, and that when we move things through the universe, we see different speeds. Now, I know there are people in the group that are going to say, well, it doesn't have to be the universe. It could be the, I forget what you call it, the Earth-centered frame. ECF, I think, is the one where certain people in the group that are GPS enthusiasts believe that the Earth may be entraining some type of a ether and dragging it with it, and that we are measuring light speeds relative to the Earth's this entrained ether, and that may be true. I can't argue against that. Or it could be that the Earth is not dragging the ether, and we're measuring relative to some universal preferred frame. And the GPS enthusiasts claim that GPS proves that it's really a Earth-based ether. But I have some, I'll probably write another paper someday showing that is not necessarily the explanation for what GPS observes, but we don't need to get into it here. The point is, though, there seems to be some ether, whether it's Earth entrained or universal. There seems to be an ether, and if you move things relative to that ether, you get differential light speed in the rest frame of whatever you're moving. Okay, and I put this into my paper, and I actually said there's anisotropic light speed, and the referees let it go through. So there we go. We've got the first, I don't know if it's the first publication, but a publication where anisotropic light speed has been recognized. Okay, that should be I was allowed to publish this instead of slowed to publish that as an autocorrect. Okay. So solve for fringe shift in the rest frame. So here's the other thing is that you can, if you use von Lau's formula to solve for fringe shift in the rest frame, you don't get it. You get a 0, as I explained earlier. So what I did is I just worked out the math in the rest frame to show that if we compute dt prime star, which again is dt, simply dt divided by gamma without this clock offset term, if we compute dt prime star plus and minus, we get the same answer as in the lab frame. And the reason, and this has been reformatted into lab frame dimensions, so we get the same answer as we get in the lab frame. And that makes sense because the fringe shift is an event. It's an event that occurs in the lab frame and in the rest frame. and the fringe shift is the same in both frames. So getting the same answer is comforting. And it also shows that speed is not c over n in the rest frame when the rest frame is moving, when it's a moving refractive medium. Okay, so now I'm going to get into speculation, and don't hold me to this. I just observed something very interesting. But again, I'm open to whatever mechanism may be causing it, but I think it's important to recognize what's interesting. So let's start with our Lorentz dt formula that we've been using all along. And let's expand it trivially. Let's just take n and write it as 1 and n minus 1. So we've separated n into two terms, 1 and n minus 1. So here's the 1 times the leading term, and here's the n minus 1 times the leading term, and here's the beta term. Okay, so same formula, just expanding it in a silly way. And then you would say, well, normally you can multiply time by light speed and you get distance. But if you do that here and you multiply this equation by c, you don't get dx. And I'll go into that a little bit more in the next slide, but it fails. So it's essentially saying light is not traveling at speed c uniformly through a refractive medium, which we know, right? We think it's traveling at another speed, c over n, or the Fresnel formula. But okay, so let's try to multiply dt by c over n. And when we do that, we also do not get dx. That fails as well. So it's saying that light is not traveling at speed c over n, and it's not traveling at speed c. Well, how fast is it traveling? So what I did is I took the three terms of the time formula, and I said, well, this term is similar to stationary refractive media. I'll multiply that by c. And this term is the beta term. This is, you're either catching your target, your beam splitter target, or it's crashing into you. This is always, you find these in these relativistic equations. This is the differential propagation length of either going toward a moving object that's moving away from you, or toward a moving object that's coming toward you, so it's plus or minus. And this is an interesting term. This is the differential the differential time caused by refraction. So in other words, n minus 1 is the increment of time attributable to the refractive medium. The 1, when I split this n into 1 and n minus 1, the 1 is vacuum, and the n minus 1 is the incremental time caused by whatever's going on in the refractive medium. And then I said, what if I multiply that by the speed v of the refractive medium, but I multiply the vacuum term by c and this crash term by c? What do I get? And so we get this formula when we multiply first term by c, second term by v, third term by c. We get this outcome, and this turns out to be the Lorentz dx formula. So we've gotten back to the Lorentz distance formula by differentially treating this refractive term, multiplying it by v instead of c. Okay, what does that mean? So it seems to mean that light is traveling at speed c through the vacuum of the refractive substance. And by vacuum, I took chemistry in college, so I think of things in terms of molecules. It's just my mental model. It may not be the model, but what I see is a sea of molecules or atoms, and light traveling between those molecules and interacting with them. But in between the molecules, I see that as vacuum or ether or whatever it is that mediates the speed of light at speed c. But I see whatever's happening between, let's call them the obstructions, just to not commit to a model. Whatever the obstructions are, I see light traveling at speed c between the obstructions. But when they encounter an obstruction, they travel at the speed of the obstruction, which is speed v, relative to the laboratory frame. And if they travel at speed v, then that fits the equation that I showed you just prior. And so what portion of the time would they travel at speed v? Well, it's n-1. And what portion of the time would they travel at speed c? Well, it would be the 1 in the vacuum term and then the beta in the beta term. And so the model that I have in my mind is that light is going through vacuum, but it's encountering obstructions. And when it encounters an obstruction, it pauses. And during that pause, it's kind of being dragged at 100% drag by the obstruction. It's not a partial drag. It's partial in time, but in that fraction of the time, that n-1 fraction of the time, it's associated with the obstruction, it's being dragged 100% at speed v. And that's how the math works out. And what's really interesting is for, n-1 is 0.5 for glass and 0.333 roughly for water. So, and refractive index of water is 1.333. So 1/4 of the time, light seems to be associated with the obstructions, and the other 3/4 of the time racing through vacuum, which I don't think that's ever. I haven't seen that as a model that anyone's presented. And what could it be? What could it be doing 1/4 of the time? The models that I've seen are, as I said, either electromagnetic models where there's a charge field, and the charge field is interacting with the electromagnetic wave that's going through. Feynman has a chapter on this, and the fellow that does the great YouTubes, the mathematical YouTubes, I'm blanking on his name right now. I just can't pull it up, but anyway, he has he covers this in stationary refractive medium, and he talks about Feynman's treatment of this, and they call it a kick. And they're saying somehow the charges that are in the refractive medium kick the electromagnetic radiation. But I don't know. I have trouble with that mechanism because it would have to kick differentially in the two different directions, and I'm not sure I'm seeing it. Nevertheless, I'm not going to take a stance. What I will take a stance on, though, is if you follow this model, light seems to be hitchhiking for 1/4 of the time and doing its own thing 3/4 of the time, which I think is novel and fascinating. Okay, so did I just go backwards here? No, I think this is that's my last slide. So this is the last slide to sum it up. So there's the Sagnac time formula on the left. I didn't treat Fizeau very fairly in this discussion. It's just not as interesting when it comes to refuting special relativity. But that's the same formula for Fizeau to compute differential time, and it follows the same principles and it works out. But what's interesting is the Fizeau formula is dependent, the fringe shift is dependent on the refractive index. And the reason is in Fizeau, you're going through different distances of water in either direction. You're either fighting the current or you're flowing with the current. And when you flow with the current, you're spending less time in the current. And when you're fighting it, you're swimming harder against the current. And so you spend more time. And so you encounter more obstructions when you're going against the current and fewer obstructions when you're flowing with the current. And so Fizeau the outcome is influenced by the refractive index, by essentially the density of the obstructions that are in the refractive substance. Whereas in Sagnac, your dx prime length, your rest frame length is the same. It's your laboratory length that's different in Sagnac. And so you encounter the same number of obstructions in the plus and minus directions in Sagnac, and so the refractive term drops out. And experimental evidence shows that refractive index has no effect on the Sagnac fringe shift, but it does have an effect on the Fizeau fringe shift. I've already said that. I've said that. Yeah, note that the non-isotropy in the rest frame is present whether the light path is linear or polygonal, or through vacuum or refractive medium. Remember, the Sagnac effect occurs in air, and it's also been shown to occur in vacuum. So you don't need a refractive medium to get the Sagnac effect. But if you get it, then it's even more interesting. My last bullet point there is that Einstein's postulates hold when the light path is two-way and when there are two clocks that are offset, but it doesn't hold for a one-way round-trip light path with only one clock. And so in summary, I think Sagnac did show that light speed is anisotropic with respect to the rest frame. And he was dismissed for many years because he used a angular motion. But when Wang et al. Came along and did it with a linear path, I think they kind of vindicated him and revealed that special relativity has certain constraints where it holds under those constraints. But if you relax those constraints, it doesn't hold. And that is my talk, Ian.
We just have to come back now. Well, thank you so much, Joe. As usual, and indeed as I expected for today, you've been very clear, and you've been very succinct as well. In fact, you've finished just under the 1 hour, so that should give us enough time to quiz you and so on. Actually, I find I call it heuristic model very, very interesting. And I'm just wondering, maybe if I could ask a general point to get things started. I'm just wondering if my own sort of analytical way of looking at it amounts to the same thing as yours, and maybe they're just looking at it from different angles, or maybe that isn't so. So when I first looked at this and found that the Sagnac effect was independent of the refractive index, well, of course, I worked out the Sagnac formula, which anybody could do. I mean, it's simple, and that's why it seems very strange when the relativist said, "Oh, special relativity doesn't apply to this. It's non-inertial motion, but just use ordinary kinematics and you get the equation." But basically, if you're looking at it from the point of view of the motion on the discs, an observer that's stationary on the disc, therefore he's moving relative to the laboratory. Well, then you have to get the difference between the constant difference, because it doesn't change. You're stationary on the disk. The constant difference divided by c plus or minus v. That's basically what you're evaluating. Now, a first glance would say, oh, just replace c with c divided by n, but that wouldn't get you independence of the refractive index. So if you consider, I hope I'm making myself clear now, but it's a bit complex. If you consider that instead of v, you'd have something like v into 1 minus 1 over n squared, which is the Fizeau drag coefficient, and then instead of c, you would have c over n. But then to that c over n plus 1 minus 1 over n squared v, you have to add or subtract the v. So that basically takes the first term up, and what you basically have is you have a c over n sort of term, and then you have a v over n squared term. Now, going back to the Fizeau formula, you'll find, the Sagnac formula, you'll find that the phase shift, or the difference in phase, or the difference in times, is proportional to v over c squared. So what you've basically done, you've modified v by v over n squared, and you've modified c by c over n, but it's c squared. So the n squareds cancel out, and you get the same thing. Now, sorry, that's a bit of a long-winded way of saying that I just substituted things in the formula and I got the answer. And I think that's probably amounts to the same as your heuristic explanation. Although what you have added this interesting phenomenon, which I'm sure people will ask about the the obstruction in the speeds, and you have a different proportion of the time for which the speed was unobstructed or was obstructed. But I suppose my quick question is that analytical analysis, just using the Sagnac formula, that you don't think that would contradict with your idea? It's probably just another way of looking at your idea.
I couldn't do all the mental math while you were talking. It was a lot. So if you draw it out, maybe we could look at it. But one of the things that we have to look at is which frame are we writing our equation in. So, if we're using the path length in the rest frame, which I call dx prime, then you have to ask whether we're looking at times in the rest frame or times in the laboratory frame, and there's going to be a gamma factor in between. Now, I don't know if that affects the math that you were just relaying to us. I'd have to look at it. Maybe you could send it to me separately, and I can give you a response.
So the gamma factor is approximately 1 because V is so much smaller than C. So you get something like 4A. It's probably omega over C squared or something like that.
Yeah,
and you can
I think
that
look at path length in your formula, and if you're in the rest frame, it should be a constant dx prime. Whereas in a Sagnac setup, whereas if you go to the lab frame, then it's dx, and it's influenced by the differential propagation in either direction. So I'd have to look at your formula to see if you're using a dx prime or a dx.
Right. But I think it must amount to the same thing because we're getting the same answers. And I mean, as you pointed out in your talk, that if you analyze it from the point of view of the observer moving on the disk or the observer in the laboratory, you must get the same phase shift. It's nonsense to say, so they must amount to the same thing. Okay, so I think with regard to your possible explanation for looking at it intuitively, there may be some questions about that. We'll just maybe quickly see are there any major questions here. Let me see, can I see them here? I have been looking at them as they come in, but I may have missed something. So let me see that we can address anything specifically. Okay. You're welcomed by Quest. Quest is going into a lot of details with regard to what he calls the invariance of C versus the non-invariance of it, and the Sagnac and so on. He's been using ChatGPT. So I don't have any specific question he wants to ask here, but I mean, he says that after all his other comments here, which you might care to read, he said, it seems that the Sagnac effect quite possibly does disprove the invariance of C, though I don't know for sure. I have discussed this quite a bit, actually, with Quest. But I think it would be correct to say, I certainly am pretty sure it does disprove, the invariance of C. And I think you would say the same thing.
I would say it does not disprove it with respect to an ether, but it does disprove it with respect to a frame moving through the ether. Right.
Yeah. This is precisely the point we have discussed. So let's.
Yeah. So if you're on the train, light is going to go at a different speed in the direction of the train or against the direction of the train. But if you're in the station, light is going to go at a constant speed relative to the air. It's the simplest way of saying.
But isn't this a natural consequence of wave motion in a medium? I mean, if we postulate a medium, because the wave is actually captured within the medium, so that's why the speed of the wave is independent of the speed of the source. But
yes, I mean
but it's not
that's one
independent of the
model.
speed of the observer.
Yeah, that's one model. And if you call the ether the medium that light is traveling through, light waves are traveling through, then it would be going at that speed in that medium. And then if you're an object that's moving through that medium, then light is traveling at different speed with respect to you, the moving object. But it's still going at the same speed relative to the medium.
Yeah. So it would be exactly the same as a sound wave in air, for example. It would
Yes.
be going at the same speed as the medium, but not if you were traveling with the medium.
Yeah.
Okay. I find this fascinating because I think we're looking at the same problem in just from different angles, and we're getting the same result. I'm actually quite convinced of this, because if you look at this logically, you must get the same result, and particularly you must get the same phase shift independent of which frame you're looking at it from. Okay, let me see anything else we can deal with before we come to the green room. Yeah, I put a note into Quest actually at the time you were talking about the two frames, just to look at it. He has done that. Okay. Let's see anything else. Yeah, actually, he just reminded me of this because I was going to ask you anyway. The videos. Could you give us, just remind us maybe, because I think you've told us before, a link to your videos?
Oh, yeah.
Ask Me Anything or something, is it?
Yeah, it's called Ask Us Whatever. It's a terrible name, but it's on YouTube, and it's all one word, Ask Us Whatever. And they are there. You know, I stand behind most of them. On some of them, I speculated a bit, and I'm not, you know, I'm probably not 100% behind the ones that claim that light can go at a different speed relative to the ether. That was a hypothetical, and I don't know that I have any evidence that that could be true. But you know, the math behind all of them is solid, and I think they really do try to frame things in a way that's easier to understand than your average physics paper. So ask us whatever.
Does it matter? Would the A in ask be uppercase?
I don't think it matters. I don't think it matters.
Well, I've just put a comment in there.
You just go to YouTube, and then
search for Ask Us.
Whatever, all one word.
Okay, all one word. Yeah. It's funny. I thought I posted that. Come up. Yes, Ask Us a YouTube video. Okay, very good. Thank you, Quest, for reminding me of that.
And there's an episode on this topic. I think it's 9.5b, and it uses hovercraft as an analogy and logs in a river. It's done in a way for high school level students, but yeah, the idea would be that the obstructing molecules are logs, and the hovercraft is trying to navigate the river, and it encounters obstructions and it creates delays.
Okay. I think it was actually Michelson's daughter, Dorothy, who, as an elderly lady, actually later on in life, she was talking about this, and she gave the analogy of, you know, two swimmers, one going with and against the stream and across the stream.
Yeah.
That sort of thing, yeah. Okay. Useful images. Okay. Okay, I think we have Jim Morrison who's come in as well. I don't know if he's in the green room. Maybe we might bring him in later if he cares to come in. Okay, let me see. There's some private chat. Now, James Keane has put in a number of statements, which I'm very happy with, because it's always good to have a sort of a heads up. He's asking about things like what about absorption emission delay in each mirror, and then the others just how we get better use ether. What is the speed in the absolute frame? So rather than try to second guess that, if I added you to the stage, and I'll try to maximize these images, I haven't done that yet. Jim, you're very welcome. Let me see.
Well, thank you, Joe, for a very interesting presentation. You're quite an imaginative guy. I'm starting to think that anisotropy is actually the rule and not the exception. Over 5-10 year periods, when I check on how many anisotropies and isotropies are listed in, say, a Wikipedia article on the same, the number of them keeps rising. And I'm beginning to wonder, is there any isotropies at all? That's not a quiet question, just a comment.
You've gone mute again, Joe. No, can't hear you. Just the moment. Did I hear something there? No. You're mute at the moment. There's a bit of a.
Did that solve it?
You're back now.
Okay, good. You know what happened? I have my iPhone close to my computer, and somehow it stole the audio. And then, yeah. So anyway, we're back. If I had a bet, and again, it's just a bet, and obviously we don't know the answer to this, but there's probably some kind of ether. Light is similar to sound waves, where it's got a wave nature to it that's going through that ether, and that ether determines its speed. There could be other influences like gravity, temperature, that could affect the speed propagation. But for the most part, I would say it's going through the ether. What do we call that speed? It's probably speed. And on Earth, we're moving through either the universal ether or we're dragging an ether with us. If we're dragging the ether with us, then light is probably going to go at speed c on the Earth. And if we are not dragging an ether with us, then we may be able to detect anisotropic light speed on the Earth. And I'll just tell you that I'm doing an experiment now in my backyard, where I happen to have a large backyard. And so I laid out a rectangle of fiber optic cables that this experiment's been going on for a year because there are a lot of variables to control. So we buried the cable 18 inches below the surface through conduit. We have two oscilloscopes, one in diagonal corners, and then pulse generators in the other corners. And we are trying to measure differential transmission of light from the pulse generators to the oscilloscopes. And so far, we have a signal, but it maps to temperature variation in the dirt. So I have not been able to eliminate temperature variation enough yet that I can conclude that I'm seeing anisotropic light speed. So we continue to put insulation over the areas to try to reduce the amount of temperature fluctuation. And there's also, because of the length of the cables, they're about 100 meters. We're looking at potentially 20 picosecond differences in transmission times, which I haven't spent a lot of time with oscilloscopes in the past, but we're right at the edges of detection, and there's a lot of noise in the signal. We are able to come up with a formula that subtracts out most of the noise, but not all of it. So actually all of it, but except for the temperature. So we'll see. Got my fingers crossed.
Yeah, right. So I mean, with radio signals over large distances, it has been validated. And indeed, this correction, the Sagnac correction, if you want to call it so, is an integral part of the GPS. So the GPS wouldn't work without it.
Let me just add, and I agree with that. So the Sagnac effect has been measured on the Earth. Michelson and Gale did it, I think it was 1927, on a very large rectangle, but they were measuring the rotation of the Earth, which is what you get with Sagnac. What I'm trying to do is measure the orbit of the Earth around the sun. So it's a slightly different setup, but so far I haven't been able to tease out the temperature effect.
Okay, well, that's a more delicate experiment. So that's basically why the MMX probably gave a very low value in the first place. It's very, very delicate. It's maybe a second order effect. Okay, Jim, anything else before we move on a bit? Have we dealt with all your questions?
Well,
you can come back if you wish.
Good. I'd like to congratulate Joe for his inquisitive nature and ingenuity in approaching some of these questions. I find this fascinating and hope that Joe will report back to us as further results materialize. Thank you very, very much, sir.
Thank you.
Okay, I second that. Thank you very much. Thank you, Jim. Now, is there anybody else in the green room? I see Vladimir is on, but a couple of other people have their cameras off. Dennis may wish to come in. I don't know if anybody else is here. No. So they're all disappearing. Okay. I don't know why they're afraid of this.
I didn't stir up too much controversy, I guess.
Yeah, exactly. Actually, Quest has actually suggested that there are very few comments coming in on the media, the social media, Facebook and YouTube, which is true. But so I think a lot of people are not here today. I don't know why, but it's a fascinating subject, and it's very fundamental to what we're looking at. Jim Morrison has asked a number of questions, or made a number of comments, which would be best dealt with through the green room. But he's come in. Are you there, Jim? Jim, are you there? No. Okay. His microphone is unmuted, but he's no camera. So. Because you may be familiar with some of Jim Morrison's ideas. He's been advocating that an MMX be done in outer space, outside, the influence of the Earth.
Yeah.
And, some other people think that would be a waste, but Jim has given, or I think, are strong reasons. Yeah, I think Jim Keane wants to come back. Yes. Hold on a second. Yeah. Okay. You're back. You're back, Jim. What's your point? Or points?
Thank you. I'm wondering if Joe would be so kind as to briefly summarize what he's trying to measure in this backyard experiment, number one. And number two, why would temperature be so important a variable?
Okay, let me answer number two first. We have fiber optic cable buried under the ground, and fiber optic cable is the rate of light speed through fiber optic cable is sensitive to temperature. So as the cable heats up, you get, I think it slows down, light speed slows down through a higher temperature fiber optic than a lower temperature. It's not a lot, but again, we're measuring picoseconds difference. And so we see it, and we actually have a beautiful sine wave, 24 hours. It's gorgeous. And I thought, oh my God, we have a real signal. But, and what excited me initially is that the signal, the sine wave, was peaking at about 10 or 11 at night. I'm like, fantastic. That's when it's cooler, and it's not peaking at 4 p.m. But it turns out that when you bury under the ground, the maximum temperature is 10 p.m. under the ground. So we had to put temperature probes under there, and it just takes a while for heat to diffuse down 18 inches. So, and unfortunately, our sine wave is perfectly aligned with the temperature that reported by these probes that we've put under the ground. So it's really just an effect on the refractive index of the fiber optic.
Well, couldn't that then be mathematically factored out to get what you might call the residual signal, which is what I think you're actually looking for here?
Yes, and that's what I'm trying to do. And it's a little too complicated for me to even explain it at 8 in the morning here in Vegas, but so we have two light paths, one heading east and one heading west, and then there are two others heading north and south on either side. And so, and we've aligned them with the velocity vector of the Earth at certain times of day. The eastward pointing light path is moving with the direction of the Earth around the sun, and the westward is counter to that. And then 12 hours later, when the Earth rotates, they switch. And so we should, if there's an effect of the speed of the Earth around the sun, we should see a 12-hour alternating signal, which we do, but it's temperature, or at least components temperature. So the problem is that there is so much noise that can come from, oscilloscope jitter, pulse generator drift, because we have two pulse generators. The thing you cannot do, you cannot use one pulse generator and one oscilloscope and go around a cycle. Otherwise, you're going to measure the Sagnac effect. We're trying to really do a Michelson-Morley experiment without using an interferometer and measuring at two locations. So, I don't want to use clocks because of the whole thing I just talked about with Einstein's clocks. So we somehow have to determine what is simultaneity. So we have the pulse generators feeding each oscilloscope. So if there's one pulse generator feeds different oscilloscopes, there's another pulse generator and it feeds those same two oscilloscopes. And then we're trying to match up the pulse signals in the oscilloscope traces so that we can look for differential propagation time at different times of day. And there's just a lot of noise, and you can subtract it all out. And we have a beautiful formula that subtracts out all of the noise, and we get this beautiful sinusoidal signal. But it's the one that gives the weakest Earth speed signal. In other words, the way the math works out, if you use the signal that subtracts out all the noise, you subtract out most of the signal as well. So what I'm trying to do is do something that will monitor the relative phases of the pulse generators. And there's a device called the time tagger that apparently counts a number of periods, and some of the more expensive time taggers can actually count phase changes between two different sources. So I may have to go to the bank and get some more money out to pay for these time taggers to try to trace the phases of the pulse generators. And if I could do that, then I can use the more powerful formula that gives me a stronger Earth signal.
But as part of the noise that you have to filter out, the effects due to the Earth's rotation.
No, the noise is really electronic in origin, and phase drift that is hard to control. But we're not measuring the Sagnac rotational effect of the Earth. We're using rotation over 12 hours to change the orientation of our cable paths relative to the Earth's orbital direction around the sun.
But would there not be a component of the Earth's rotation?
Yes, you're right.
In that?
Yes, it'll add or subtract, but it's small. I think the Earth's rotation is about 500 kilometers per second, whereas its orbit is 30,000 kilometers per second. I'm sorry, 500 meters per second, and the orbital speed is 30,000
kilometers
per second. Yeah. So there is a rotational component, but it's very small compared to the orbital speed. And then originally we didn't bury the cable very well. And we had a signal that was 10 times what we thought we should get. And it's like, oh my God, we must be moving relative to the CMBR at 300,000 meters per second because of the signal we saw. But then we realized, temperature was potentially affecting it. And so we've done all this insulation now to try to reduce the temperature. And Jim, you're absolutely right. We've reduced the size of the sinusoidal signal by reducing the temperature variation, but I'm not yet at the level where I've reduced the electronic noise enough to see the Earth signal rising above that.
Interestingly enough, one of the dismissals, I suppose, over the years of Miller's results was the temperature effect, which it was attributed would make a very big difference. But I think in his case, actually, he took great precautions to avoid major radiative effects and so on, insulation and all that. But it obviously is important, in some way or other. Okay, Jim, anything else before we move on a little now?
No, thank you for listening to my question and addressing it. Thank you.
Well, thank you for bringing in those interesting questions. Now, Jim Morrison is here, and Jim, I know you alluded to some of the points which you've been making in recent times to us, but would you like to expand on them and maybe put some of the points to Joe and maybe ask what his response is?
Can you hear me okay?
Yeah, I can hear you perfectly, yes.
Hi, I'm the guy you were probably mentioning as a GPS enthusiast.
Okay.
But you weren't here earlier, yes.
By the way, I was having some technical problems, so I didn't really hear the discussion about your experiment. But have you heard of an experiment done by a guy named Krischer in 1995?
No.
Because it sounds a lot like what you seem to be talking about.
I will have to look that up.
How do you spell that, Jim?
Krisher.
1995. I'll look it up. I'm not aware of it.
Well, anyway, he used an optical fiber cable that's part of a antenna array, radio antenna array, 21 kilometers long, looking for a difference in phase over time between microwave signals sent down the wire, down the cable, back and forth. Didn't find anything.
He didn't find anything?
Right.
Okay.
So if the propagation frame for EM near the Earth is the ECI, a local ether, a local propagation frame, that essentially, I guess you could call it entrained by the Earth, but it doesn't rotate with the Earth. That's a crucial difference. It's fixed in direction. And it has a variable density according to a theory by a guy by the name of Ching-Chuan Su. You might be curious about checking his theories out too. He actually proposed a theory he called the local ether, where the ether has a variable density proportional to the Earth's gravity, to any celestial body's. Jesus, I'm having trouble talking too. Gravitational potential. So kind of defines a sphere of influence around each celestial body. So it only extends for the Earth out to about 1 million miles, L2 essentially, where the sun's gravitational potential becomes dominant. And then within the sun's reference frame, or I should say, the sun has its own local ether in effect. And under that hypothesis or theory or paradigm, the Earth's rotation would not have any effect on a single back and forth.
I agree. That's my fear.
Okay.
Yeah, but I understand, and that's essentially what the experiment is all about. Is there and I'll tell you why I'm investing time in it, because I alluded to this. I think there's another potential explanation to GPS, and maybe sometime we can talk offline. But if you believe in time dilation in proportion to speed, then the various satellites and clocks that are used in GPS are not all traveling at the same speed relative to, let's call it, the universal frame. When they're rotating one direction with the Earth and the sun's orbit, they may be going a little bit faster, just like Ian mentioned that the rotational effect can add or subtract from the translation speed. And so you could be getting differential time dilation of the clocks that are being used in a GPS measurement. And if you're getting differential time dilation, it could be compensating for anisotropy in communication speed. Just like in an Einstein setup where, the clocks are being offset to compensate for anisotropy, there's a natural clock offset effect just that comes from time dilation. There's a theory called slow clock transport. Have you heard of that?
Yes.
Yeah. And so slow clock transport can actually give you an offset between two clocks that have been separated. So I'm just wondering if that's been thought through entirely in these GPS experiments of whether, differential speed through the universe against the universal preferred frame could be causing some slow clock transport offsets in the GPS clock measurements, and whether that is masking anisotropy.
Well, actually, this Cheng Chuan Su derived an effect of the velocity of GPS clock versus the ECI, which is what is operationally used. Essentially, it's the absolute speed of the satellite relative to the ECI that determines its dependence on tick rate.
Okay.
That's, by the way, HSU, isn't it? That man.
No, it's just
No, it's SU.
SU.
Oh, okay, yeah.
SU.
SU, okay.
If
I
you
will
want,
look that
I can send you references. I think you might find it interesting, at least.
Yeah,
You know,
for sure. Yeah.
Especially since you seem to be willing to think outside the box.
This whole subject, just one might say in parentheses, it seems to be.
I have a video on CNPS from about a year ago, I guess. We talked about it, but
yeah, you talked about it yourself. Yeah. No, I'm just thinking of all this possible masking of effects. Ostensibly getting zero results for MMX, and
I'm sorry.
It seems to be a subject where one thing is sort of compensating for the other. Maybe the very talk that Joe has given us today is an example of that, where possibly we have a compensation of effects, which results in an independence of the refractive index for the Sagnac effect, which it seems to fly in the face of one's first analysis, but when it looks in more detail, one perhaps gets different results. Okay, it's the old the White Knight again, Lewis Carroll. But I was thinking of a plan to dye one's whiskers green and always use so large a fan that they could not be seen. That's the same thing.
Anyway,
Well, so that's very interesting, Jim. Thank you very much. I think the point you addressed there were the ones you put in the comments in here. So I think,
Right.
Yeah, that's great. That's excellent.
Thank you, Jim. I'm going to look
Sure.
up those papers for sure.
Yeah. Okay. Well, you've got even this Chris Her reference is new to me. So thank you very much. So Jim, anything else before we move on? We've got a little time left.
That's enough for now.
Okay, if you want to come back before we leave, you're very welcome. Thank you very much, Jim. Okay. I don't know if Dennis Allen has come in. He seems to be there, but don't know if there you are. Denny, I'm taking the liberty of putting you up because I just what would be your reaction, first of all, to Joe's ideas as expressed today? I have discussed this whole subject with you at length. And,
there seems to be a lot of agreement between what you maintain and what Joe maintains.
I agree. Yeah, and it's interesting to have your observation of that.
Wesley in his book, what's the name of this book? Scientific Physics by J.P. Wesley, 2000.
Yes.
He talks about the absolute evidence for absolute space in chapter 1, which would be his ether. His ether would be absolute space. And he gives, at the end, on page 46, at the end of the chapter 1, he gives various experiments and how they all seem to add up to pretty much the same thing, the same speed of the Earth through the solar system through the universe, and the same speed and the same direction too. So it'd be a velocity effect, not just a speed effect. And I don't know if this book is not well known. It's old now, 2002. But the roughly the speed through the universe of the solar system is about 360 plus or minus 40 kilometers per second. And it gives a direction too, but I won't go into that.
Is this relative to the CMBR?
Yes.
Yes. Yeah.
I beg your pardon?
It's relative to the cosmic microwave background radiation.
Well, that's one of the tests, yes, but he shows that, well, here, let me go through them. The galactic redshift, with one of his things he checks out, 2.7 K background anisotropy. That's another situation. The anisotropy of light velocity of coupled mirrors and toothed wheels, 2 experiments by Marinoff, Stefan Marinoff.
Yeah.
The geostationary satellite signals, Muller and Means. And finally, the muon flux entropy by Monstein and Wesley. Monstein was a Swiss electrical engineer who was tied in closely with Wesley. He ran into trouble with a German judge and who threatened him with jail and a terrible fine. He didn't stop his research, so he moved to Switzerland.
Yeah, you said he's still around, although I think he's backed out a bit, whereas Wesley is deceased. Isn't that so?
Yes, that's right. Wesley died in 2006, I think.
Okay.
Anyway, this book is over $50, but I think that if you plead poverty or something of the sort, they'll give it to you for much cheaper because it's so old, you know.
Are you familiar with Wesley's works, Joe?
No.
J.P. Wesley.
I'm
Okay.
gonna get the book.
Look, we always hope. You've given us so much today that if we can pay you back even at a very small proportion of what you gave us, they would be delighted by giving you one or two references. J.P. Wesley would be one.
Yeah, all these things that I mentioned all give roughly the same velocity of the solar system through the universe, which is really amazing because they're all different. They're all over the map, so to speak, but yet they give the same result pretty much.
Okay.
Yeah.
Yeah, that speed apparently fits with the dipole, the CMBR dipole that they see in the redshift and blue shift in the CMBR.
Yes, I think that's one of the things he uses.
But isn't there, I haven't followed this too closely, this thing called the Hubble tension, where that does not agree with the CMBR number? I'm not up to speed on it, but apparently in the Hubble tension, that is the expansion of the universe. That's different than the speed.
Wesley, pardon me, I didn't mean to interrupt. Wesley does not agree that the universe is expanding, and neither do you, Ian, right?
Yes, quite so, Danny. But I mean, Harry's sessions on Sundays, we've been talking about this Hubble tension, and Vladimir, who's with us, I don't know if he's still there, has written a paper on this. But basically, if you just do some measurements of redshift against what we believe are the distances of these objects using Cepheid variables and other means and so on, and assume a linear law, well, you get a particular value. But then if you use the accepted model of the early universe, if you believe in expansion and Big Bang, which, as you say, Denny, we don't, or many of us don't, I don't, and Wesley and so on, you get a different value, which might be, I don't know, one might be 73 kilometers per second per megaparsec, and the other might be 69 or something, which is quite a distance. So there's something fundamentally wrong, perhaps. I would say, anyway, humbly, that it's their whole model, it's their whole linear.
They assume it's expanding because of the redshift, but there's, that's just one item.
And they've extrapolated that back to zero.
You used Hertz's EM theory as opposed to Maxwell's. Right?
Yes, that's true.
And Hertz was the one who invented radio transmission.
Yeah, it was a modification.
Some poor fool who, came along and then passed on, and thank God he's gone, sort of thing.
Sorry, who's that, Denny?
Hertz.
I missed something. You said so. Oh, you said something. Thank God he's gone or something. That you're referring to Hertz, are you?
Well, a lot of people don't pay any attention to Hertz. He wrote 2 books, one on radio transmission, which started the radio transmission, and verified Maxwell's theory that it should be possible. And he wrote another one on classical mechanics in a new form, I think it's although that's a translation from the German. Both are essentially ignored today.
See, he is rather well known for having demonstrated Maxwell's ideas of electromagnetic radiation transmission and reception, but it's not known that he was actually quite a significant theoretician as well. And the books that you've mentioned would be an example of that. It's not known.
Well, the problem was he was down in his basement all the time doing measurements on the speed of light and so on, and he apparently got cancer as a result.
Because he died in his 30s, I think. Yes.
Yeah, and people had to finish up his books, at least the one on Newtonian classical mechanics. He couldn't finish it up; he was too ill.
I didn't realize that.
Yeah, he was. He spent too much time. He was in a basement which had basically a brick wall or a concrete wall, and the waves would bounce back and forth a number of times before they died out. And So he became cancer-ridden, apparently.
Okay.
And so he didn't, he wasn't around to defend his theory.
Yeah, but it has been resurrected to a certain extent in many ways. And this business, was my own hobby horse that I think you're referring to, about the use of the total derivative, which we use in hydrodynamics. We don't use a simple, if we're differentiating something, we're concerned not only with the partial derivative, but if there's a movement in space, we have to take that account as well. That it's basically a divergence, the divergence of the particle. So it's using Eulerian or Lagrangian hydrodynamics. Well, if we apply that to electromagnetics, to electrodynamics, we get a fuller expression. And in fact, we find that the ordinary Newtonian or Galilean transformations applied to these modified Maxwell equations give invariance. So you don't need a Lorentz transformations. Well, so that's I think what we were talking about.
Ian, why don't you send your papers to Joe?
Yeah, I'd be happy to do that. I can.
Great.
Yeah. Okay. I'll send. I have your email. Yeah. Okay. So yeah, well, thanks for bringing all those things to our attention, Denny. Anything else before we might have time for one more contribution? We'll probably wrap up then.
Well, I guess I should let someone else talk.
Yeah, well, no, thanks very much. Actually, I'm surprised that we don't have more people in the green room now. Sometimes people don't come in at the very beginning. They're following it on the media, but they come in at the very end. So actually, I thought we had Cornelis, but I think he's gone, and Vladimir's gone. So we have a gentleman with there, Carl Riff, but he never comes in on the camera. I think his system doesn't permit it, but he's listening intently. So we may get some response. By the way, your paper, Joe, which I had a look at myself, in fact, I think I downloaded it here. I think you gave a link to that at some stage. Your recently published paper, which they published, as you say, because they didn't know who you are.
Right.
So just remind us of that.
It's in European Journal of Physics in February of this year.
Okay. Is it downloadable by an ordinary member of the public?
Oh yeah, it's online. It's open access. So
yeah, exactly. That's
you
how
can
I
just
got
search
it.
my last name, February 2026, European Journal of Physics, and it'll come up.
Okay.
And it starts out with the title "Deconstruction of Light Speed."
Yeah. So, if I may, I mean, I try not to give my own opinion too much, but I think that the vast majority of what you've said and you've put in your paper and all that is as far as we know in science, it's beyond reasonable doubt. You're logical and you're looking at the results and you're looking at what actually happens in practice. And we have a lot of experiments using the Sagnac effect and so on. But the part where you're looking at it heuristically, well, that's the word I was using, to see why or how the light does this and the differing velocities and the n1, n-1 or that sort of thing. That's the only part which might be a bit speculative.
Oh, it is speculative.
Yeah, okay.
It's certainly speculative. What I find fascinating though is as I said, in water, 1/4 of the time it's not moving, or it's moving at speed v, the speed of the water. What is it doing during that time? And the other model is, well, it's just the entire time it's moving more slowly, but that doesn't track with the experimental data. The experimental data shows that it's apparently delayed when it's encountering whatever obstructions there are in the medium. So I don't know what that mechanism could be, but
Yeah, and as you started your lecture, I mean, I used the word speculative. Well, I don't mean it in a pejorative sense. I mean, you pointed out that we don't actually know the exact mechanism
Right.
which reduces the speed in the first place in a refractive medium.
Yeah.
Well,
And you gave a number of possibilities, but we don't know.
well, there's such a thing as Bergman-Allen electron and proton modeling that might throw some light on that. They either model as spinning rings of charge, either positive or negative,
Yeah.
whether it's a proton or a neutron or electron. Neutrons are modeled too, and this spinning ring of charge is stable because the magnetic field is such that it pinches the charge inward with the same force that it expands outward during Coulomb's, because of Coulomb's law. And so if it was in one of these protons or electrons, then it would tend to move relative to the electric field, which would be the velocity of the, in the case of water, would be velocity of the atoms of water.
Yeah.
And so you might be able to explain it that way. I don't know.
Mm-hmm.
But by the way, you know, of course, Joe, that the recordings of these meetings will be available immediately. It'll be, you know, so the last talk, actually, technical talk we had 2 weeks ago was by Dennis himself and David Bauer. And you're giving part 2 of that talk next month, actually. So look out for that. Using your own Bergman-Allen model.
Yeah,
Okay.
I mean,
yeah, go ahead, Joe.
conclude with, you know, again, I don't know what the model is. All I recognize is the phenomenon. But you know, it does raise the question of, if light is just a wave, then why is it pausing? You know, what is going on there? And could there be, and I'm not saying it's a particle or a wave or both, whatever, but could there be some kind of interaction with the molecules or the atoms in the substance or the subatomic particles where, you know, there's a hesitation or a pause for a very short period of time before it moves on? And I don't think a lot is known about that. You know,
And I don't think the question has even been put. I think you're the one, the first one who's perhaps done that.
yeah.
They just
So
gone with
that's my contribution for the day.
Okay, well, thank you very much, and thank you, Denny. Anything else before we have to wrap up now?
No, I think that's about it.
Well,
And by the
thank you
way-
very much.
Very much for your presentation, Joe.
Thank you. Thank you. I see that James is thinking about my backyard experiment a little bit more, and he wrote a note. And James,
Well,
I think
good.
it's a great idea to try to do it at high temp or in a metal pipe on the surface and see if that can change the timing of the temperature effect versus the earth effect. Great idea.
Oh yes, he's put a comment in. Yeah, okay, very good. Okay, well, thank you very much. Well, I'd like to give some minutes, basically to you, Joe, because I'd like you to summarize. Well, you might say I've said everything, nothing more to say, but in the light of the discussions we've had and the questions which have been put, and you know, there's never an end to it, you might want to summarize the situation and maybe give us a pointer as to what might lie in the future with your experiments and with your other ideas. And then, so I'll give you the floor for a minute or up to 5 minutes, whatever you wish, to say anything more. And then I'll come back and officially close the meeting. So is that all right? The floor will be yours.
I don't have too much more to say. I think I've said just about everything. But, you know, to summarize, I think the important part is that Sagnac did show that light speed is anisotropic with respect to the moving observer. It's still consistent with the notion that light speed is constant in whatever medium it is transmitted through. But with respect to an observer that's moving in that medium, light speed is anisotropic. And I think Wang et al. Showed that that happens in a linear setup and doesn't need rotation in order to manifest. People love to say, well, Einstein was wrong, or Einstein is never wrong. I think it's somewhere in the middle. I think Einstein did lay out his conditions, and he did talk about two clocks, and he talked about how they should be synchronized. So he thought it through, and my beef with that is it is written in such a cryptic way in Einstein's 1905 paper that almost everybody misses it. But basically what Einstein has been saying is if you set the clocks so that they report different times, then when you make one-way measurements using those clocks, you're going to get a constant light speed. But it's really deceptive because the clocks are not reporting the same time. So it's playing with our concept of simultaneity. Other than that, so I'm not saying Einstein was wrong from this paper. I'm simply saying that he played with the clocks in a way that didn't always reach discussion level, and that's why he can claim that light speed's isotropic in all frames if you use his clocks. But if you don't use his clocks, as Fizeau and Sagnac showed, then it demonstrates that light speed is anisotropic. And that's about it. And I'll let you know if my backyard experiment turns up anything.
Well, please do. Please keep us in touch. So it devolves upon me. We're coming to an end now, and we could talk about this for a long more time. I hope actually we have an opportunity. I hope Joe, I'm sure he will keep us up to date on his backyard experiment and his future work in this area and any further publications, because I found them all most interesting. And do keep an eye on his website, Ask Us Whatever. But I'd like to express our deep gratitude to Joe on behalf of the CNPS for having agreed to give us this talk today and having prepared all the background information, because he did a lot of work, especially for today, to make it clear to us. He could have just said, go away and read the paper. But I found it very illuminating that he had described in detail the background to all this. And thank you very much for fielding all the questions and for the discussions. So we hope to keep in touch with you, that you will participate in some of our further talks. And indeed that as things develop in the future, you'll come back to us and give us another talk on further developments in this area. As I said at the very beginning, it seems to be a rather thorn in the side of the simplistic analysis of phenomena, not making a distinction between the constant light speed relative to the source, if the source is moving, as distinct from whether the observer is moving, and people conflating these ideas. And it appears to me, anyway, from the analysis that I've done, that the Sagnac effect does produce these results, which Joe has explained in very great detail and measured and analyzed and so on. And it also indicates not only that there's an anisotropy with regard to the motion, the observer, which is in motion on the disk, but there's also it indicates, actually, by the by, that the light speed is actually constant independent of the source, because you don't get that factor coming in, and it's quite clear. And the experiments of Rudong Wang et al., which Joe did refer to, are quite illuminating in that respect, and bringing this to a linear system, and therefore contradicting the quick dismissal of this as being non-linear, and therefore something one cannot really talk about in terms of relativity. So thank you so much, Joe, again, for coming along and doing that. Thank you, everybody else, as well, for your questions and for your attention. And if you have any further ideas which didn't occur to you as the talk progressed. I'm sure if you submitted them to us, we'd be happy to forward them to Joe, and Joe would be happy to come back. Or even if you want to keep in touch with Joe, I'm sure he'd be quite happy to discuss any other matters relative to his ideas of deconstruction light speeds in moving refractive media. Very interesting and important subject. So I shall wish you, wherever you are on the earth, probably mostly in the Western Hemisphere, a very good day. And we look forward to renewing our acquaintance with all of you through further talk, particularly on Saturday in a short period of time. So goodbye. Thank you all again.